Good morning, folks. This is lecture 3 of the mechanical vibration course. So what we have on the agenda today is to discuss the concept of damping, and in particular, viscous damping situation. And then once we do that, then we go and uh, get the solution and discuss the damp-free vibration of a mass spring damper system, or a single degree of freedom damp system. Okay. Now, we have a mass and spring, and let me see if I can have the drawing here. Mass and spring, as shown on the left-hand side, and now we add a damper, and the damper is of very special type. And what that means is that we are assuming that the viscous damping, in other words, the velocity of the mass m describes the force by the damper resisting the motion of the object. Okay. Now we are assuming that in this particular drawing, for example, there is no friction between the mass and the surface that it's lying on, or this can be also turned around and made it hang from the ceiling, for example. And in that case, of course, there is no issue of the friction involved. So anyway, we have to draw the free body diagram of the block, and assuming that the coordinate system that we use is shown on the top left side. The forces in the vertical direction are the weight of the object due to gravity, and the normal reaction force that is exerted by the ground on the block, preventing it to go through it, of course, through the ground. Now, the horizontally, spring always resists the motion, and damper that we're introducing here, which is drawn in the symbol below, is resisting motion. Therefore, they're pointing to the left, assuming that the block is displaced from the equilibrium position, to the right by the amount x. Okay. Before I actually derive the equation and everything, let me remind you that a damper, a viscous damper, such as what you have for your handheld bicycle pump, for example, is basically a container. And in the container, there is an enclosure. There's a piston. There's a piston that can go back and forth. And in the piston, there are little holes, and this is all submerged in let's say, a material which is viscous, such as oil. And as you try to push the left-hand side, or as you hold the left-hand side and try to move the handle on the right side, the fluid from one side has to go through these holes to the other side, and you know that there is always the viscosity in a fluid, and therefore that creates a friction force that prevents or obstructs the motion of the piston inside. That's the whole idea behind a viscous damper, and that's mainly why the symbol associated with viscous damping, as you see on the top left. Okay. A good example here is, for example, what is used in a suspension of a vehicle. You can see that, for example, this configuration that you see actually is right here. Okay. That's one way of employing this in real life. Now, the drawing is done here once again for your convenience, and we know that because the equilibrium is from the motion is from the equilibrium position for convenience, so the values of spring force, resisting spring force, and resisting damper force can easily be drawn or written, as you see in a second. Newton's second law says sum of all the forces, and the only forces in the horizontal direction that are acting here are Fc and Fk, both pointing to the left, opposite to the direction of the positive coordinate system, and therefore minus Fc and minus Fk on one side. This is sum of all the forces, equal to mass times acceleration, and there is your mass times acceleration. Now, because we're dealing with a viscous damper, the assumption is that the force in the damper is proportional to the velocity. As I mentioned, if you have a bicycle pump, and if you want to move the handle very slowly, there is not much resistance by the pump that you feel by your hand. But if you try to push it really fast, then you see that it requires some force in order to hold the pump from moving away. So the unit for C is either kilogram per second. If you just go and put all the units here, in other words, Newton, for example, if FC is in Newton and X dot is meters per second, and you basically look at the unit for C, is either going to be Newton second over minute, Newton second per meter, or kilogram per second. Incidentally, some textbooks, they don't use the letter C, they use the letter B. Okay, just keep that in mind. And the spring force is simply Kx. We are assuming that X is the amount of stretching from the equilibrium position. Okay, that's why this is the case. Now, if you plug these two into the top equation and take everything to the left-hand side, you get the mother of all equations where the damping term is present. Now, we have dealt with this last week, except that we assumed there was no damping and therefore there was no Cx dot term. But here we do have Cx dot. Now, your math prof, back in the second year differential equations course, it took a lot of, it took some time in order to show you how the solution to this looks like. By the way, please go ahead and look at the last 20 minutes of the video on YouTube, which were posted on lecture 1, week 1, lecture 1. You will notice that I went through the solution of stuff like this, okay? And although when I followed the instructions that your math prof provided you, it didn't quite look like this. It was actually the sum of a sine and a cosine, etc., and there's exponential, but that can be massaged and factored out, grouped, so that the solution to this equation looks like what you see on the right-hand side. Now, just be careful here. We know it has e to the some exponential, or e to some power with a negative sign. We know that it's sine, and some textbook may be using cosine depending on development. This is how our Inman's textbook does it. What we don't know in this expression is A, well, we don't know what zeta is. We don't know what omega n, we know actually what it is, because omega n was called the natural frequency. And if you assume that, for example, this Cx dot is not there, it's the equation that we derived and worked with in lecture 2, okay, week 1, lecture 2. But that omega n came out to be what is called the natural frequency, which was the square root of k over m. But we don't know what A is, we don't know what omega d is, and we don't know what this phi is. Don't think that this A is the same A that we got in lecture 2, because there was no damping present. There was an expression for A, but this A is not that same A. And this phi, the phase angle, is also not that same phase angle. We'll get these things. Now, right there. In order for me to convince you that this A is that expression and that phi is this expression, well, I have to spend about 10-15 minutes of basically becomes a differential equations course, which I don't intend to do. If you have any issues with that, please go ahead and review some of the stuff that we did at the end of lecture 1, or grab a textbook on differential equation and just look at the part that we solve second order linear constant coefficient problem, which is this. Now, notice that in the expression for A, whatever this zeta is and whatever this omega d is, let's not worry about that right now. We have V naught, and we had that in lecture 2. We have X naught, and we had that in lecture 2. Okay. In the expression for phi, also, we have V naught and X naught. So when there is no damping, this term zeta is 0, and you can just cross this out. This 0 times that You can cross it out. And same thing down here. And in that situation, omega d is omega n. So if you leave out anything that has zeta here, this term and that term, and every omega d replace it with omega n, you get exactly what we got in lecture 2. Okay? Right. All right. That's what we had for omega n, right? Natural frequency of the vibration. Now, zeta, I'm going to tell you what the value of it is, okay? But I will get there for you. I will show you where the zeta is coming from, okay? Zeta is called the damping ratio, and unit less, and it's the ratio of this C divided what is called a critical damping, which is, for example, 2m omega n. So this zeta is nothing but C over C critical, and this C critical is 2m omega n. Once again, I want to tell you that some of these concepts not quite clear. Why am I taking all this stuff and coming up with somehow zeta? You just have to be patient, that's all. And this omega d is the damped natural frequency. Omega n is the natural frequency, undamped natural frequency. And this omega d is the damped natural frequency, which is omega n times a number which is 1 minus zeta squared. Okay. In the event that zeta is 0, omega d is the same as omega n. Or if zeta is small, omega d is close to omega n, but not necessarily the same. Now, sometimes this thing that you see here, C over 2m omega n, or C over C critical, sometimes you write it a different way, because if you substitute omega n from that expression, you get 2 square root of km, which is fine. I mean, zeta is equal to C over 2 square root of km. All right. So first of all, let's do an example and work with some of these numbers. And then after a few slides, I will show you where in the world is this zeta coming into the picture, because this is what we have. Right now, you take it for granted that the solution for this is right there, where the values of A, phi, zeta, and omega d is down here. So let's go ahead and do an example. We have a setup like so. Consider an initially undamped mass spring system right there. A damper is then added, so that is down below. For what value of damping ratio zeta will the damped natural frequency omega d is 90% of the undamped natural frequency? So remember, we have an omega d and we have an omega n, okay? Omega d and omega n are related by taking omega n and multiplying it by square root of 1 minus zeta squared, okay? So what we want is omega d to be 90% of omega n. So it says, what is the value of damping which makes this thing true? All right. So first of all, let us write the expression for omega d, which is right here. And I want this expression to be 90% of omega n, or 0.9 omega n. Just plug it in. Omega n cancels from both sides. Solve for zeta, and this is the answer to part A. Okay? Then, in part B, it says, if the mass is 10 and the stiffness of the spring 10 kilogram and the stiffness of the spring is 10,000 Newton per meter, what is the value of C? Okay, this is called damping ratio, but that doesn't tell me what the value of C is. I mean, immediately you have to do some calculation. You cannot, it may be that if you looked at, for example, hypothetically on a pump, it may give you the value of C if you're lucky, or the data sheet for it here, but it may not give you the value of zeta. So I want to know what the value of C is. Okay. So first of all, I mean, it's a fairly straightforward way. You write the expression for zeta. zeta is C over C critical, or C over 2 square root of mk. Remember, there are two ways of writing this thing. It is also possible to write this thing as 2m omega n, right? 2m omega n, which is the same thing. Now, we plug in the stuff that you know. We just calculated zeta right there. We have m, we have k, get the value of c, and this is the value of c in this unit. Okay? All right. So that takes care of our first problem, which was fairly straightforward. Let's move on. So the question is, what is this? What is this zeta? What is the effect of this zeta on the response of the system? Okay, damping ratio on the response of the system. Okay. First of all, I guarantee you, if zeta is between 0 and 1, okay, in other words, that combination, that the mass damping and stiffness that you have in your expression for zeta, that combination makes zeta between 0 and 1. The solution, the response, or the motion of the mass, block of mass, as a function of time, looks like this. This is called an underdamped system. Okay? So the choice of M, K, and C, if it's such that they put zeta between 0 and 1, the solution X, as a function of time, will eventually die down, oscillates and die down. There are a few things about the oscillation of this that I'm going to talk about later on. Okay. Now, in a sense, the damping ratio determines the rate of decay. You will see that. The closer the value of zeta to 1, the closer the zeta is to 1, the faster this thing will decay. Okay, but still oscillatory. All right. Now, this kind of a damped system, underdamped is the most common occurrence in vibration in real life. Okay, let's move on. Suppose the values of Ck and M will give you a zeta damping ratio which is bigger than 1. And if you plotted the response of the mass, response of the space, response of the mass, which means displacement of the mass as a function of time. Ultimately, that's what you want. You have a differential equation, the mother of all equation, where the unknown is x of t. It's a differential equation. You have to solve it. So it's the x of t that you want. That's why I say the response of the mass, displacement of the mass will look like that. This is the case where zeta is bigger than 1. Now, which one of these could it be? Well, that depends on the initial conditions. Remember, uh, if you were able to solve that equation, you need initial conditions to be able to plot it. Depending on what the initial conditions are, here is displacement, here is the velocity. You may get, for example, in the first case, is this? Notice that the displacement is 0.3. You can see that. This is 0.3 millimeters, for example. Velocity is 0 because the tangent to this curve at the top seems to be 0. Okay. Then this case is displacement is 0, but there's a velocity, there's a slope here. And finally, displacement is minus 0.3 and no displacement. In all cases, the solution is not oscillatory and it dies down. We can see that. As time goes on, x goes to 0. This is called an overdamped system. Okay, so there's no oscillation, and the object always will actually come to a rest, but after an infinite length of time. Okay, after real life is not like that, but anyway, at least theoretically, it'll take forever for this thing to come to the equilibrium position, which is 0 position. Now, the case where zeta is equal to 1, very specific choice of CMK, where if zeta equal to 1, is what you call critically damped. The solution is also coming down to 0 in an infinite length of time, but I mean, which one of these it looks like depends on the initial condition. Notice that for this case 3, it may even cross the axis and then come down, okay, depending on the size of the velocity and direction of it. So the point is that critically damped and over damped, the behavior is the same. Eventually, it comes to a rest. Eventually, it comes to a rest without any oscillation, okay? But the case of underdamped, it also eventually becomes to rest. Eventually means after uh, uh, infinite number of seconds, but it is oscillatory. That's the main difference between it. Now, how we distinguish or differentiate this case overdamped with the critically damped, this case critically damped with the overdamped that we did in the previous slide, there's several ways to describe it. So I want to go through them. It is the smallest value of zeta that gives you non-oscillatory solution. This zeta equal to 1 is the smallest value that you can have so that you don't have any oscillation. Because remember, if zeta is any less than 1, anything smaller than 1 is going to have oscillation. Okay? If zeta is anything bigger than 1, it also damps out without oscillation. So zeta equal to 1 is the smallest value of damping ratio which does this. And another way of describing it, it basically separates non-oscillatory from oscillatory response. Because if zeta is less than 1, involves oscillation. If zeta is bigger than 1, there is no oscillation. So it separates the non-oscillatory from oscillatory response. Okay? And notice that in the case of critically damped, this is critically damped, and overdamped where zeta was bigger than 1, the solution, of course, in both cases, the solution goes to 0. You can see that. But this goes to 0 faster than the overdamped situation. In fact, it is the fastest way to go to 0 without any oscillation. Okay, so and these say the same thing. They all kind of describe this concept of critical dampness in 3 different ways, 3 different sentences. All right. Okay. So what is this zeta thingy? Okay. Oh, hang in there. Yeah. Uh, this explanation of where the zeta is coming from. Okay. How did zeta pop into that mother of all equation ABC or not ABC MC and K is going to be very important when we do multi-degree of freedom systems, okay, later in the course, the last 3 weeks of the course. Remember, the mother of all equation for a damped vibration is this. I can divide through by M, and immediately you notice that this thing here, you notice that it's actually omega n squared, okay? And this expression, if you define zeta the way I gave you, in other words, zeta equal to C divided by 2 square root of Kf. If you use that definition of C, the solution can be written nicely like that. In other words, coefficient of 1 here, omega n squared in front of x, and this expression in the middle, C over M, is 2 zeta omega n. Let me say it a different way. When you look at the mother of all equation, you have 3 physical parameters, M, C, and K. 3 physical parameters. But you can rewrite the equation so that the response, or X, only depends on 2 parameters, response parameters. One of them is called omega n, the other one is zeta. From 3 things, you essentially go to 2 things, zeta and omega n. Okay? All right. It makes it a lot nicer. This makes it a lot cleaner. And when we try to solve this, if you had this equation and you wanted to solve it mathematically from differential equations, of course, or that equation, there's less work to be done when you deal with this. Okay, good. Let's move on. All right. So what I want to do is uh, I want to uh, write the solution. Write the solution to your differential equation. Remember, I already alluded to what the solution of the equation is. I told you, please take it for granted. This was my original equation. This is the massaged version of it. Okay. And I want to write the solution to this guy. You see that? The solution to this fellow. This fellow does not have MC and K. It has zeta and omega n. That's it, as far as the parameters is concerned. So I said, take it for granted. The solution looks like this. Okay? Where A is given here, and the phase angle is given there. Notice that, first of all, in this solution, I said that, yes, you have zeta, you have A and phi that you're going to get. You also have omega D, and omega D was the natural, the damp natural frequency, right? Okay, but notice that we have both omega D and omega N. So this is the solution when damping damping ratio is less than 1. If the damping ratio is less than 1, there you are. And that's the only thing that I gave you right now. In other words, if the damping ratio is less than 1, there's a solution. I haven't told you what the solution is when the damping ratio is equal to 1 or bigger than 1. I haven't told you that. Okay? Now let me put this stuff together. I'm going to put this stuff together. There we are. Okay. Now, what do I mean by how does this look like so? How does this look like so? Well, let me tell you what Inman has done. Sine of something plus something else. Sine of omega d plus phi. Sine of something plus something else. Sine of alpha plus beta. In trigonometry, we could take that sine of alpha plus beta and write it as sine of alpha cosine of beta plus sine of beta cosine of alpha, right? So if you use that expansion and do a little bit of cleanup, this big box, as it is here, reduces to the box below it. Am I saying this is better than that? No. Am I saying this is easier than that? No. It's just an alternative way of writing this big box. So, two ways of the solution to this equation, the mother of all equation, the second form after I divided by m, right there, second equation, this equation. Two forms of the solution to this equation if the damping ratio less than 1, okay, or under damped system, okay. So let's move on. And keep in mind that both of these, omega d and omega n, appear here. Now, what if the damping ratio is bigger than 1? In other words, an overdamped system. Okay. If the solution is overdamped, please go and look at the case at the last 20 minutes of the lecture 1, or review your differential equations book on this subject. Only 2-3 weeks of it that you need. Now, if it's an overdamped system, there is no sine or cosine. There is no sinusoidal motion. So take it for granted that the solution to the mother-of-all equation, if zeta is bigger than 1, is right here. It has two exponential terms. See that? Both of these are, there is no sine or cosine here. There is two exponential terms. One of them is out here as a factor, okay? And the other ones are inside of this bracket, right there. So notice that here is this expression has a t in it, minus zeta omega and t. The expression inside will have something similar to that, except that it's actually not omega n, it's omega n times square root of something, okay? And this thing, the whole thing here is usually your omega d right there. Now, A1 and A2 depends on the initial conditions, and they're listed here. So if I give you x naught and v naught, and if you know that zeta is bigger than 1, here is A1, here is A2, get these things, stick it in that equation, and you have your response. Okay? Zeta bigger than 1, overdamped system. Now, in the special case that zeta is equal to 1, in other words, critically damped, of course, this is not going to be true anymore. This is not going to be a solution anymore. The last 20 minutes of lecture 1 or differential equations tell you what you're going to get as the solution to the mother-of-all equation. So if damping ratio is equal to 1, take it for granted, go figure it out. The solution is a combination of constant, depending on the initial condition, another constant, depending on the initial condition, time t, time with decay term. All right? These have nothing to do with this course per se. These are the stuff that you did in your second year, and I reviewed it for you in the last 20 minutes of lecture 1. There. So we got everything. We got the solution when it's underdamped, overdamped, critically damped. In terms of the two response parameters, that's a fancy way of referring to zeta and omega n, by the way. And the initial condition, or affecting the coefficients that make that solution, both in these two cases, and of course in the case of underdamped also. All right, let's do a problem. Okay, so let's go ahead and do an example which deals with some of these things that we just introduced. Suppose you take the human uh, leg, okay, and one has done an experiment to figure out that if the knee is in the locked position, this position, not bent, locked position, and the axial vibration of this is just like a spring. This is just like a spring, a fancy spring, very complicated fancy spring. The axial vibration of this, okay, if you look at it as a mass spring system, also a damper system, of course, because of the fact that this is a complicated situation, and they have found the natural frequency of this, natural frequency of axial vibration of this leg configuration is 20 hertz. Okay. Now, suppose we also know that the damping ratio for this human leg is 0.224. Suppose these are obtained by experimentation. Okay, these can be obtained by experimentation. Okay. All right. So let's move on. Now, suppose this fancy mass spring damper system, okay, is given a source from an equilibrium position, you can visualize that here's a spring, here is a damper, and here is a mass. You can visualize it like that. Suppose this mass is given an initial velocity of 0.6 meters per second from the equilibrium position. Okay, what you would like to know is basically the response. We would like to know the response of the leg, the response of the mass. Now, you might say, wait a minute, what does that mean? Initial velocity, the mass is given initial velocity of 0.6 meters per second and zero initial condition. Actually, this zero initial condition, that's a bad way of saying it, should have zero initial displacement, not initial condition. That's about, this is a typo. Okay. Now, let me give you an example. Suppose this fellow jumps on the ground, okay? That ground will give the mass, the foot, the bottom of the foot of this guy is a velocity because it's kind of an impact load. Okay, landing at our feet with a knee in the lock position from a height of 18 millimeter. Obviously, if you jump from a height of 180 millimeter, you're going to break a lot of stuff. Okay, so 18 millimeter is going to give you basically some non-broken pieces. So this condition, zero initial displacement, which is meaning that it moves from equilibrium position, an initial velocity of 0.6 meter per second corresponds to jumping average person on the ground from a height of 18 millimeters. Okay, that impact load essentially causes a velocity, initial velocity of that. Let's move on. So that's part A. It says calculate response, means give me the solution of x versus time. X is response of the leg. Remember, I visualize this thing as mass and damper, spring and damper and mass down here. Okay, and part B is what is the maximum acceleration experienced by the person without any damping. Okay, let's not worry about B right now. Let's worry about A. So basically, you have to tell me what is the value of x of t as a function of time. And we already had several slides. You go back 2 slides ago, the whole thing was given. If you're dealing with zeta equal to 0.224, we are dealing with an underdamped position, an oscillatory motion, of course. Now, remember, I need omega n because the solution depends on zeta and omega n. But this is Fn. This is omega n, but not in radians per second. That's what we want. So let's first of all multiply it by 2 pi. Take this 20 hertz, multiply by 2 pi. You get the natural frequency of this mass spring damper system in radians per second. Okay, so that's first step. Now we know zeta underdamped. So we have an omega d. Plug it in. There is the omega d. We calculated omega n. We were given zeta. Just plug it in, and you're going to get omega d equal to 122.4. Now, notice that the damped natural frequency, the damped oscillation frequency, is going to be smaller, not necessarily always a lot smaller, but smaller than the undamped natural frequency. This is the undamped natural frequency. This is the damped natural frequency. This is going to be smaller than that because that formula says it all. 1 minus something. Okay, it's just a matter of going to that slide and writing everything down. We know zeta. It was given to us. We were given omega n after we converted to radians per second. We just calculated omega d. So what is to be found? A and phi. A and phi depend on initial conditions, initial velocity, initial displacement. And needless to say that we were told that things start from there. We can measure things from the equilibrium position. X naught is 0. And you are told that the initial velocity is 0.6 meter per second. Jumping from a height of 18 millimeter will give you that condition. Okay, just plug it in. If you take these things and stick it into A and phi, this is what you're going to get. All right. You can write your solution. Just write your solution. A is this number sitting right there. E to the, we have zeta, we have omega, and multiply that, you get this times t. Sine and phi was 0. Notice that phi came out to be 0, so we don't have to worry about it. There we are. Okay. Now, if when there's no damping, omega d and omega n are the same, and you know, just look at the condition that we have here. If you look at this expression, just look at this expression, right there. See that? Right there. If there is no damping, this term is not there. This term is not there. You see that? This term is not there. Zeta is 0. Okay. And if your initial condition x naught is 0, this is not there. So basically, we have v naught squared over omega n squared, because omega d and omega n are the same. So we have square root of v naught squared over omega n squared, which, right there. And you get like so. Okay. So there we are. And we are asked to find the maximum acceleration. So the maximum acceleration is x double dot peak, right? Now, I didn't have to do that. I know from lecture 1, what this is. It is a omega n squared, right there. Okay, right there. But if you don't believe me, take this x, differentiate it twice, and look at the thing that's in front of sine. You're going to get a omega n squared. Okay? Look, peak acceleration is amplitude or peak displacement. This is the peak displacement times omega n squared. Oops. And you can plot it. There we are. This plot is the plot of x of t as a function of time. X of t as a function of time. There we are. Okay, so another example. So what we have is a weight of 10 pounds suspended from a spring. We have the stiffness of the spring, that's 30. And we know that it's critically damped. So this C is not quite arbitrary. Okay, we know what the value of C is because we know that the value of zeta is equal to 1. All right. The weight is given an initial displacement of 2 inches from its equilibrium position and suddenly release. Okay, so when you do this configuration, this is going to be sitting at some location. That's what we call equilibrium position. Suppose we bring that thing down by the amount 2 inches and let it go. Obviously, it starts oscillating back and forth. And common sense tells you that, common sense and observation tells you it's going to be oscillatory, obviously. And we are asked to find, first of all, the damping coefficient based on the information that's given, C, and the displacement after 0.01 second, 0.1 second, and 1 second. Okay. As far as getting the value of C is concerned, that's not a big deal because we know that it's critically damped. Write the expression between zeta, m, c, and k. Right there. And you're going to get your value. But we don't have to do it like this. We can do it a different way. In other words, look, you know that zeta is equal to c over 2 square root of mk. You agree? So you know everything except c. You can plug in there to get the value of c. But there's another way I can look at the problem. I don't have a control on how you're going to do that. I want to show you different ways of looking at it. To get the value of c, you can just go through the straight calculation. straightforward calculation. But I'm going to look at it a different way. First of all, look at what it says. We have the weight, 10 pounds. We have the gravity, assuming that we are on Earth, so we can find the mass of the object right there. And then we just stick it into that formula, and get your omega n. You know K, you just found M, and you're going to get this, okay? But at the critically damped condition, critically damped condition, means zeta is equal to 1. So you write the expression for zeta this way, either this or that. And because of what I did, omega n I have, m I have, zeta is equal to 1, and you're going to get your value of C. Now, the alternative way of doing that was to say, okay, zeta is equal to this thing on the right hand side. Okay, this thing, I know the value of m, calculate. I know the value of k, I don't know zeta, and get C. So the first couple of minutes when I was talking about this problem, it says, maybe that's the way I do it. Or this is another way of looking at the problem. Okay. In other words, find omega n first, and then use this. Same thing. You do it any way you want. Okay. And this is the value of C. Now, the case where we have a critically damped condition, we have the solution. Go back to a previous slide or 2 slides ago, and you have your solution. It looked like this. This was for critically damped oscillation. Well, there is no oscillation, critically damped system. Okay. Value of A1 and A2 depend on your initial condition. Please go back 3 slides, find out that this was X naught, and this was V naught plus omega n X naught. And I know everything in here, and therefore I can plug it in. I was told that the mass is displaced by 2 inches and released from the rest condition. So all the stuff that you know, just literally write it down, and there's your response. And you can find response after 0.1 second, 0.01 second, etc. But at 0.01 second is this, at 0.1 second is there, and after a long, long time, very, very tiny value, because we know that this thing goes to 0 after infinite length of time. And you can plot it right there. So this was my second problem. Let's go and do the third problem. Okay, this is the third and final example that we're going to be doing today, and it's taken out of somebody's work up there. What we have is a door that is equipped with a mechanism. As you can see here, these are very common. You can see it on the door out here in the room. Embedded with a torsional spring, because this door actually rotates, trying to open and close. Therefore, there's a torsional spring in there and a torsional damper. And the function of the spring and the damper is basically to close the door. Okay. Now, some information about the door is given. The mass of the door is 50 kilograms. And if you take that door, because it's a rectangular shape, for example, it has 2 moments of inertia. One is about the vertical axis, another one about the horizontal axis. So the one about the vertical axis, which is the parallel axis to the door axis, is 7.5 kilogram per meter square. Now we're going to come to these things in a minute, okay? In the next slide, you're going to see these things in shape. So the height of the door, the height of the door is 2, and the width of it is 1, and the mass moment of inertia about the axis in the vertical direction, through the centroid, we are told that it's 7.5 kilogram per kilogram meter square, not per kilogram meter square. And you're also given some information about the torsional stiffness of the spring. is given that. So the first question is, what kind of a damping coefficient, what kind of damping coefficient do I need in order to make this thing a critically damped condition? Okay. So the reason is that you want the door, for example, to close as fast as possible, right? That's the whole purpose of these dampers, to bring it back to the closing position, for example, in the most in the fastest possible way. That's why it says critical damping. And then let's worry about part B later on. We're going to worry about part B later on. Okay. So write the equation of motion, the mother of all equations. What is the response variable? Well, it's not a translation of a mass or a translation of the door. It's the rotational position of the door. So this is the mother of all equation, where instead of x, I'm using the variable theta to remind you that you're interested in the angular position of the door, and therefore theta double dot, and theta. And in front of these things, because these are angles, theta double dot from your dynamics class, you don't multiply that thing by m, mass of the door. You multiply it by mass moment of inertia about the axis of rotation. Axis of rotation is vertical, so this is the mass moment of inertia about the axis of the rotation, which is this vertical axis of the door. This vertical axis of the door. And there is a CT that we have to find. We have to find CT. It says, what is the damping coefficient to have critical damping? Okay? We want to find CT. And we are given KT. We're given KT, is this number, 25 Newton meter square per radian. Okay, so first of all, this, because rotation is taking place about the hinge position, I have to take the mass moment of inertia, which was given to me about the vertical axis through the centroid. See that? Through the centroid, and convert that using parallel axis theorem to the mass moment of inertia about the hinge where the rotation is taking place. I see that's 7.5 plus the mass of the door times the distance between the two axes. And we'll worry about these things in a minute. Okay, so there it is. So this IA is not just the mass, or it's not just the 7.5. It's using the parallel axis theorem, because this is about the axis of rotation. This thing, we don't know what it is, but we know that the resisting torque is this number times theta dot. That basically, that's just to remind you where this is coming from. This is the resisting torque. And that guy, of course, we know what it is. Resisting displacement. Displacement here means angular displacement. Resisting torque. And of course, IA, we just talked about it. So, so the configuration, if you look at it from the top, what we see is the door, 1 meter like that, two in the length direction, that I'm going to draw that for you in a second. We have a spring here, and we have a damper. We have a spring and the damper. And the theta is this angle that we are using in the mother of all equations. Now, here's the situation. This is the axis of rotation, 1 meter wide, 2 meter high, and we were told that the mass moment of inertia with the axis to the centroid, not through the axis of rotation, but through the centroid, which is exactly halfway between these two vertical edges, is some number, 7.5. Okay? So this is torque, because we're dealing with a rotational system. In general, we have, for example, translational distance is going to be proportional to velocity. Here's proportional to angular velocity. And this is the situation. The mass moment of inertia about this vertical axis, the dashed vertical axis, was 7.5. But there is a distance between this vertical axis and the axis of rotation. That's where we have to use the parallel axis theorem. This number 2, this height of 2 does not come directly into our calculation, but it affects, of course, the mass of the object, right? We are told that the plan is to have critical damping, 0 equal to 1. And why critical damping? Because we want the door to be closed or to close as fast as possible. Please go back to when we discussed the undamped vibration, underdamped vibration, or critically damped vibration, or overdamped. And I talked about the critical damping corresponds to the case where the response goes to 0 as fast as possible. We want the door to close as fast as possible. Okay? All right, good. So we know zeta is equal to 1, and that means critical damping and the actual damping are the same. Remember, the definition of zeta is C over C critical, or in this case, because we're dealing with a rotational motion or rotational motion, CT over CT critical. Okay, this is that condition, because zeta is CT over CT critical. Okay. So incidentally, we know everything here, no problem, except that this has to be worked out. Okay, we just discussed it. So I about the axis of rotation, just make sure you're using consistent unit. This number was given to us. The mass of the door is m, and the distance from between the two parallel axes is 0.5. So it's just going to be 20 kilogram meters. So the mother of all equation, which can be written like that, or it can be written like this, is a second order linear constant coefficient problem, which is written here. Now, when you look at either this expression or that expression, it doesn't matter. You know that the natural frequency is this number, k, divided by m. We don't have k and m, we have k, t, and I. So you just plug it in, okay? And zeta is CT over CT critical. Same formulas that we used before, except that the roles are rotational here. CT over, you can write it as 2 square root of, remember it was mk, 2 square root of mk, but we don't have m and k here. We have a different animals, so 2 square root of mass moment of inertia times the torsional stiffness, or you could have written it like that. Either way, CT over 2 IA omega. And these are the same thing, except that in one of them I used the expression right above it in order to eliminate the other variable. Okay, so let's find out the natural frequency. KT was given to us. IA we just calculated a minute ago. It was this. We know there is critical damping here, so zeta is equal to 1. We don't know what CT is. We want to find this other stuff we all know. We just calculated it. So 1 equal to CT divided by 20 was from the previous slide. It's right here. And omega, and I just calculated. Remember, here I can also say 2 square root of IA times KT. That's the same thing. And that'll give you the value of CT. Okay? That answers the first question. Now, what's this second part? Okay, so imagine you want to go through the door. So you come, you put your hand on the door, and you give it a push. Okay? That creates an initial condition. If that push is very small, the door does not open. If it's too big, then it's going to open and slams the door on the other side, in a sense, on the wall. So the question is, what initial velocity, that you putting your hand on the door and pushing it, it gives you that initial velocity. The question is, oh, by the way, so if you do it very give it small velocity, the door doesn't open up. If you push it too hard, okay, the door opens too much unnecessarily. What you want to do is to give it an initial velocity so that it opens up by maximum of 70. Once it opens 70, you can jump out of the room and the door will close. That's what you want. Okay, so you want the maximum opening of the door to be 70 degrees. Find the initial velocity of that you have to give it the door. So we don't know what this thing is. Okay, we don't know what this thing is, but we know that this is a critically damped system. Remember, we designed our torsional damper to satisfy this condition. Okay. So, and we know that the solution for this case, the solution for a critically damped system is right here. Please go and check your formula. You may not see theta there, you may see x, but this is not a translational motion, this is the rotational motion, therefore write theta equal to this. This is on your slides. Okay, written here again. Well, first of all, we are opening it from the equilibrium position, which means initial angle is 0. Okay? And if you take this and stick it in that expression, if you said theta equal to 0, left side is 0, right side, you work it out, you get A1 equal to 0. Notice that when T is 0, this is 0. So this A1 better be 0 so that you get the 0 on the left side. Now, we don't know what this thing is. We don't know what the initial condition is. But what we know is that the maximum angle theta, I want it to be 70 degrees. Okay? So, first thing I'm going to do, I want an expression for the maximum value of the angle of theta. So how do we find the maximum value of something? Anything. You differentiate with respect to the variable. So here is time is the variable, and I want theta dot to be maximum. I want the maximum theta dot to be 70 degrees, by the way. So how do I find how do you identify the time that it takes the door reach its maximum opening position, right? So isn't it true that to find the place where theta is maximum, I have to take theta dot and set it equal to 0, right? Because you want to find the maximum value of theta. How do you find maximum value of theta of something? Differentiate it. Okay. So, well, first of all, if you do that, differentiate this theta that incidentally we found A1 is 0 in it. There is no A1 anymore. So you get this. Okay. Now, if we set theta, if we set t equal to 0 here, we're going to get, you see that? This theta dot at 0, you just plug it in. Just plug it in. You get theta dot at 0 equal to, if you set t equal to 0, this will go away. This becomes a 1, and you get that. So this A2 that you see there, A1 we already know it's 0, right there. A2 is actually that maximum initial velocity that we don't know. This is the thing that we don't know. So this A2 is exactly the thing that we want to find anyway. So if you replace instead of A2, instead of A2 you write theta dot of 0, the thing that we want is going to be right there. We don't know what it is, but it's going to be right there. Okay, so the question is, after how many seconds you reach this maximum value? How do you find the maximum value? You differentiate it, you set it equal to 0, and find the t. So this is no big deal. Okay, look, I want this thing to find after how many seconds, after how many seconds this thing becomes a maximum. Well, how do I do that? Once again, I just told you a minute ago that you differentiate this thing and set it equal to 0, right? And so let's do this. Set it equal to 0, you're going to get this equation. Well, I don't know what theta dot 0 is. I don't know this thing. But one thing is for sure, out of this, I can find the value of t. This can be solved for t. So it says the maximum opening of the door is reached after that many seconds. After that many seconds. After that many seconds. So if you take this guy and stick it in there, and your theta is 70 degrees, you can find theta naught dot. Okay? All right? So here's what I did. I took this time and plugged it into that fact. I don't know what theta dot 0 is, but I know that after that many seconds, this must be the maximum value of theta, and I want that thing to be 70, right? I want that thing to be 70 degrees, right there. Don't use degrees because these are all radians, so 70 degrees times 2 pi over 360. So it's this number, 70 degrees right there, 70 degrees right there is that many radians. So you just plug it in, and this e to the minus 1 comes from the fact that you're taking this number, stick it in there, and you're multiplying by omega n. So you get minus 1, right? This thing is, when t is that, is minus 1. What is the unknown here? The only unknown that I have is theta dot 0. And that's the thing that we were asked to find. So this person, or you, if you want to open the door, let me go back to that last slide. You have to push it so that it imparts an initial angular velocity of 3.75 rad per second. Okay, folks, so that wraps up the lecture for today. See you on Thursday.